You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Linda J. Spilker. Dr. Linda Spilker is a JPL Fellow, Senior Research Scientist and Planetary Scientist at NASA's Jet Propulsion Laboratory, who has participated in NASA and international planetary missions for over 45 years. She is currently serving as the Voyager Project Scientist. Her mission roles have grown to encompass mission leadership, as well as design, planning, operation, and scientific data analysis. Prior to Voyager, she was the Cassini Project Scientist, leading a team of over 300 international scientists to maximize the scientific return of the Cassini mission within the cost and schedule. She worked in a science role on the Cassini project for 30 years and was co-investigator with the Cassini Composite Infrared Spectrometer team. She led the Sears Ring team, focusing on thermal infrared studies and modeling of Saturn's rings to address questions of the ring's origin and evolution. Remember to subscribe to Event Horizon so you never miss an episode.
Dr. Linda Spilker, welcome back to the program.
It's a pleasure to be here, John.
Now, when we last talked, Voyager 1 was having some issues, and you guys were working hard, much effort in trying to get it back. What's the update? Where is it now?
Well, let me just go back a little bit. Turns out that in November of 2023, we were looking for our Voyager data just like we usually would, and we didn't see any data coming back. We just heard a tone from the carrier. And it's kind of like receiving a letter and you open it up and the pages are blank. So we had no information that we could really use to diagnose what the problem was. And through some extremely clever detective work, the flight engineers were able to determine that the problem was with one of the flight computers. And I mean, Voyager has worked well for decades, and there have been small problems along the way, but this certainly was one of the most significant. And so it was pouring through many of the good records, old memos, it's sort of like searching for a needle in a haystack for some clues. We even got some retirees to come back and help. And they tried different telemetry modes and slowly built up a story that they saw evidence of this software problem. And eventually we were able to get Voyager to provide us with a memory readout. It went through every location in each of its computer memories, and we could compare it to what we had on the ground. And we found that there was one corrupted block, a block of memory that had failed 256 words. And that memory had held a lot of important information, that piece of it. And so what we were able to do is to program around it, that piece of memory. We used other places in the memory. And so this was really, if you think about it, it's the first time we've actually put together a software patch on something that's outside the solar system. It took us about 6 months to fix it. And on April 20th, I remember that morning as we waited eagerly for the Voyager information to come back, suddenly the blank letter had words. And Voyager 1 was communicating again, and cheers went up throughout the room. And, you know, those Voyager engineers are a lot like space cowboys. They had figured it out.
And what's the health of the spacecraft now? Is it back to where it was before the hiccup?
Yes, Voyager 1 is operating normally. Both Voyager spacecraft are working just fine at this point. And we've had other little hiccups along the way, but certainly that one that occurred, over almost a year ago was the most significant one that we've had so far.
Now, Voyager 1's trajectory was very different past the gas giants than Voyager 2 because, as I recall, they wanted to take a look at Titan, and that required sending the spacecraft off into a trajectory where it couldn't go to the ice giants. It had to go off in a different direction out of the solar system. What is the benefit of having gone in that direction? Because Voyager 1 was the first to pass, the heliopause or something like that. What was the advantage there of actually sending that off in that different direction and have it leave the solar system faster than its twin?
Well, when the two Voyager spacecraft launched, we had no idea that they would last more than 45 years and actually end up outside the solar system. And so our initial science goals, and you're right, with Voyager 1, was to fly close to Saturn's moon. Our goal was to fly close to Saturn's moon Titan and really study this very interesting world. It had a thick nitrogen atmosphere, We couldn't see through to the surface, and we thought maybe Voyager could see through to the surface. And that wasn't possible with that close flyby. We had the opportunity with Voyager 2 to also fly by Titan if we had found something really incredible. But since we couldn't see the surface, then we decided to continue on with our plan to send Voyager 2 on to Uranus and Neptune. Now, Voyager 1 flew very close to Jupiter in particular with what we call a gravity assist. And so those close flybys of two big planets, Jupiter and Saturn, gave it a tremendous amount of additional velocity that allowed it to leave the solar system. And it was going faster than Voyager 2. So Voyager 1 was the first spacecraft to cross the heliopause and leave our solar system, cross that boundary, the boundary between the sun's influence and interstellar space, and then start exploring for the very first time what it was like outside that boundary.
Later, some years later, and you were deeply involved in this, Cassini went to Saturn and took a look at Titan and was able to actually drop a probe onto it, which was quite amazing. I remember there were snafus with one of the two channels involving it, but otherwise we got a picture of the surface of Titan. And now we know that the hypothesis at the time of the hydrocarbon liquids on the surface of this world turned out to be the case, that they are there.
Right, that's correct.
Well, what was that like, as before we even knew that, what was that like, just seeing the smog, the orange smog and saying, man, I really wish, because I remember people had hypotheses back then about that the fluids on the surface of this body. What was that sort of like?
Yes, there's intense interest in Titan and trying to see through to the surface. And there were ideas that maybe Titan was covered with a global ocean of hydrocarbons, all sorts of theories and ideas. And so it's disappointing. We didn't have the instruments or the filters on the cameras to see through that photochemical smog. But the benefit was almost immediately after the Voyager 1 flyby, a group of scientists got together and approached NASA and the European Space Agency and said, we need to go back to Saturn and we need to carry a probe and we really need to explore this very fascinating world that in some ways, kind of like the Peter Pan of the solar system, maybe it was what the early Earth might have been like. And so they made the case based on the Voyager data or the lack of data from Voyager that we needed another mission called Cassini, and NASA agreed. And hence we did have another chance to go back to Saturn, carrying now with the instruments that could see through to the surface, landing on the surface with Huygens, and also carrying filters on the cameras that could see through to the surface as well.
How long did Huygens last on the surface?
That's a good question. I don't have the exact answer. Let's see. I think the Huygens probe was actually sending back a signal for several hours from the surface of Titan until its batteries were depleted. And then it now is just there resting on the surface of Titan. But it sent back information from the surface. When it actually touched down, we could actually watch the shadow of the parachute from the Huygens probe go across, make direct measurements of the atmosphere, and actually probe a little bit about the surface as well by sending out this surface science package. And so just in that first landing on a moon in the outer solar system, we learned so much about Titan. And then over the 13 years of the Cassini mission, followed up and really had a chance to explore that very interesting world.
It'd be interesting, and something that I've thought about just musing is what Huygens looks like now, because Titan appears to have some weather. I mean, there is some kind of rainfall there, or at least an analog to a water cycle, only it's hydrocarbons. It'd be interesting to see if that thing's coated in ice or what's happened to it since. Any ideas?
It would be quite interesting. You're absolutely right that there's weather on Titan, that methane plays the role that water plays here on the Earth. And so it's very cold on the surface. Perhaps it's rained methane onto the Huygens probe, or it's been covered with other hydrocarbons that form in the upper atmosphere and have fallen out. And perhaps it has sort of like the equivalent of a light coating of snow on it. That's as slowly as building up with time, where I'm not sure how quickly it would build up, but just sort of slowly burying the Huygens probe. We know that it landed in a dry stream bed. And so it'd be very interesting. I mean, I don't think there's a mission to go back to visit Titan. It's called Dragonfly. It's with what's called an octocopter that will actually go parachute down to the surface and then use these rotor blades to actually fly from place to place. But I don't think a visit to the Huygens probe is currently in its flight plan.
Probably not, but it's fun to think about, especially since that's such a
Yeah,
living world. It's and in a lot of ways, Titan being one of the most alien vistas that you can think of in the solar system, also looks eerily like Earth in some ways, just at way lower temperatures. And but you still have that regime of liquid moving around. The dry riverbeds, as you mentioned, and lakes. And it's weird how similar it is yet dissimilar. And tantalizingly, people have brought up the idea of life at low temperature, microbes, and then also deep below the surface. I believe in ammonia water slush, perhaps. So it's a really amazing world and well worth going back. So I'm hoping for the quadcopter, just because of the success of the one on Mars. The drone we had, and I would like to do that in more places. And you can imagine the pictures that'll come back, because the ones from Huygens of those sort of coastlines that it showed were just amazing.
absolutely. And then the methane lakes and seas at the North Pole of Titan that were there that we could see in the radar experiment, just these reservoirs of hydrocarbons. And could there be some kind of methane-based life rather than water-based life?
Only one way to find out. Go there.
Yeah, go back.
Now, we are coming up on an anniversary, the pale blue dot, which is one of the most iconic photographs in astronomy. And who could forget Carl Sagan waxing poetically about it, saying that, everything, everyone, and everything that's ever happened with humanity happened on that little blue dot. I think he called it a speck of dust suspended in a sunbeam. When is the anniversary, and what's planned, if anything?
Well, we're coming up on the 35th anniversary of taking the family portrait, those group of pictures that Voyager snapped. The original images were taken on Valentine's Day in 1990. And there's an interesting story behind that because, as you indicated, Voyager 1 only flew by Jupiter and Saturn, and then its trajectory was bent up out of the plane of the planets. And so it had no planetary encounters after that. And so Carl Sagan started working after the Saturn flyby to convince the project that we needed to do something like this, to take the Voyager cameras, turn back, and take snapshots of the planets that we could see. And at the time, there was a lot going on, planning for Uranus and Neptune. And so initially, the project just said, we have a lot on our plate, and we don't see any giant scientific value in doing that. And I think he tried requesting it something like 7 times. And finally, I think he went back and he made his case to NASA headquarters as well, and they decided it was a good idea. And so it's now 1990. We've flown by Neptune in 1989. So basically, the planetary phase of the Voyager mission is over. The mission is downsizing significantly, just thinking that the operation of the spacecraft will only last a few more years. And so they said, yeah, turn the cameras back on for one last time and take this series of images. And so we saw Uranus and Neptune, Jupiter and Saturn, Mars and the Earth. That the Venus and Mercury were not visible from the cameras at that time. And so we took these series of images, and the one of the Earth in particular is really, really spectacular. Turns out that the Earth, is relatively close to the sun, so there was a lot of scattered light creating what looked like sunbeams in the image. And inside of one of those sunbeams is the Earth, this pale blue dot that Carl Sagan talked about. And you're right, his iconic and very poetic saying, about this is the only world that has life in our solar system. And I think from the vantage point of looking back from such a great distance, that we could really appreciate, this is a world that basically contains all the life that we know in our solar system. And it looks so tiny in that sunbeam and really, so precious.
Bizarre question. So I guess the data, once it's transmitted, a picture like pale blue dot is gone on the spacecraft, right? It gets erased and replaced with other data. So it's not actually still on the spacecraft for an alien to find.
That's correct. Yes. We overwrote those pictures. We probably overwrote them many times. It turns out that Voyager has an 8-track tape recorder. So over the decades since we took that image, we've written a lot of information about interstellar space across those images. But Voyager does carry a golden record. And while the pale blue dot image, of course, is not on the golden record, there are sights and sounds of Earth, images of different places on the planet, and we even included a cartridge to use to play the golden record. On the cover is sort of a pictorial step-by-step. Here's how you play the record. Here's where you put the stylus. If you get the first picture right, it's going to be a circle, etc. It's made of gold because we think that'll probably last something like 1 billion years. So that'll give time for the Voyagers much, say 40,000 years or so. They'll pass relatively close to different stars. It just depends. They're so tiny and they'll be very cold, whether or not some other civilization might find them and find the record and go back and try and play it. On the cover of the record is actually a diagram of how to find the Earth as well. So that would be very exciting.
Yeah, doesn't that involve pulsars? In other words, here's, in relation to these 13 pulsars, there's Earth?
That's correct. So putting Earth in the center of that group of pulsars and trying to indicate their distances, etc., and coding their rotation periods to tell you just where to go and find the Earth.
Now, onto your specialty, planetary ring systems. Now, through Voyager, that was really the first close looks that we saw of the rings of Saturn. What were we able to learn from the Voyagers before Cassini about the ring system of Saturn? In other words, when you guys started Cassini, what did you already know?
As we started Cassini, we knew that Saturn's rings were made up of lots of individual, look like individual ringlets, but incredible amount of structure. That going in, I remember with the Voyager flybys, we thought maybe the rings would be these bland sheets of material, but far from it. It turns out there are gravitational interactions with the tiny moons that orbit just outside the rings, and other kinds of dynamical effects that create really very beautiful structures in the rings. And so it's just quite a surprise to see the amount of detailed structure. Also finding these gaps inside the rings, and one of them actually had a moon inside. And so just really opening our eyes to what the rings really truly look like and getting some of the colors of the rings for the first time. And Cassini then could go on to build on that and understand a bit better about, if you could hold a ring particle in your hand, what would it look like? Would it be like a fluffy snowball or a hard-packed ice cube? And we know now it's probably a lot more like a fluffy snowball. And this idea that maybe the ring particles grow into bigger aggregates, like maybe even the equivalent of house-sized or bigger ring particles. But then perhaps over time, those aggregates break apart and come together, and that there's this active process going on in the rings, perhaps very similar to the disk of material from which the planets formed. So we can use Saturn's rings as a natural laboratory to try and understand how moons and planets would form in our solar system. And then, of course, getting the composition of the rings. Not only are they water ice, mostly water ice, but these non-icy contaminants that come in as micrometeorites and hit the ring particles and stick to them, and getting the age of the ring. So we think, one idea we think now from Cassini data that perhaps the rings are only a few 100 million years old, and maybe there's ring systems might form and then dissipate with time. So just lots of interesting information building on what Voyager found initially, and then the 13 years that Cassini spent in orbit to really expand our understanding of the rings, the moons, the planet, of the whole Saturn system itself.
Now, are extensive ring systems in the past that have dissipated possible around the other planets? In other words, might even Earth or Jupiter once have sported an extensive ring system that's just simply gone now?
And yes, that's a possibility. Jupiter has some very tenuous rings around it, but the source of those particles is primarily the tiny moons that orbit in close to Jupiter. And so once those moons have been eroded away by various processes, then the ring system at Jupiter will probably be gone. And then Uranus and Neptune each have ring systems of their own. Uranus, there are these very narrow, dark rings, very different from Saturn's rings. In other words, there are narrow rings with lots of space in between them. And perhaps that's just evidence of maybe an older ring system where not as much material is left over. It just depends on the processes from which you think a ring forms. If a moon's broken apart, or a comet might be broken apart, and then those particles spread out to create the rings. And then Neptune has a smaller ring system, but that's in part because its large moon Triton was captured. It's a captured object in a retrograde orbit, and probably in the process of being captured and the orbit circularizing, actually probably devoured some of the rings that were there at Neptune. So it's left with some rings and even some very interesting ring arcs, just what are brighter patches in the rings that we actually had seen a little bit about from Earth and that the Voyager took the first pictures of. And so that was fascinating to see as well.
Yeah, and that was the Triton is another one, yet another surprising moon that Voyager 2 saw that had cryovolcanism going on actively on its surface. What you would think is the frozen, dead outer solar system, it turns out it isn't. It's very dynamic out there, and it just works at much lower temperatures. But interesting things happen. And then we saw Pluto, and that that sort of blew it out of the water, saying, yeah, it's way more interesting out there than you ever thought. But that was one of the great things about Voyagers were just constant surprises. Almost everything that they saw was surprising.
Yeah, I think with Voyager, being the first certainly has its advantage. And being the first to fly by each of these 4 planets, there were just so many discoveries made. And at the same time, a long list of questions left for future missions to go back to answer. But you're right, at every single flyby, there were new discoveries made. Active volcanoes on the surface of Jupiter's moon Io, bright white Enceladus sitting in the midst of the E-ring at Saturn, and then just the ring system and the other interesting moons itself. Uranus with its fascinating rings and being tipped on its side, and a tiny moon Ariel that might be an ocean world in its own right, similar to Enceladus and Europa. And then, of course, at Neptune, Triton, so it seems like the moons and these potential ocean worlds, in a sense, were sort of the stars of the Voyager show in just helping us better understand that maybe you don't have to keep life in what you'd call the Goldilocks zone, in that region where water could be a liquid on the surface of a planet. Maybe instead, in these oceans underneath the icy crusts of these moons, you might have conditions that are right for life. And that's just so fascinating to contemplate.
Yeah, and then there were some of the sort of forgotten ones that might also be ice shell moons. We don't know, but it seems to be possible. And they're moons like Oberon, where, yeah, we saw it, but we still don't know a lot. But what we did see was tantalizing, and now it just sort of fell off the table, so to speak.
Right, right. And at Uranus, since Uranus was tipped on its side, Voyager saw the south pole of Uranus, but only the south poles of the moons. And so there are the other sides of those worlds we didn't get a view of because they were in darkness. And, just amazing moons like Miranda that looks like some giant hands have torn it apart and then thrown it back together. And cryovolcanism that might be present on Ariel, maybe on Oberon, Titania, some of the other worlds. But to go back with the instruments like Cassini had and at higher resolution and go into orbit and really, really study the Uranus system. In fact, the most recent planetary decadal survey selected Uranus as the next flagship mission. So Uranus orbiter with probe would carry an atmospheric probe to send into the atmosphere of Uranus itself and spend many years in orbit, as Cassini did, really studying this ice giant system and seeing how different it might be to the gas giants Jupiter and Saturn.
And the great question, what knocked Uranus on its side? What in the history of that planet happened to force it into that situation? What are the hypotheses right now on what forced Uranus to be this way?
Probably the leading hypothesis might be that there was some kind of violent collision that tipped Uranus on its side early on, because the rings and the moons that formed from probably that disk of debris left after Uranus formed are all in the equatorial plane. And so those had to form after the planet itself was tipped over, and then you had the rest of the system form.
Now, what's the radiation environment at the ice giants like as compared to Jupiter's gigantic radiation torus that's it's just unbelievable. But what's the radiation environment from the planet Uranus like?
There is a radiation environment there, but since the planet is smaller, it doesn't have as strong of a magnetic field and intense of a field as Jupiter has. And so you don't have those radiation belts present. Although we didn't get in, I think, really close enough with Voyager to know for sure. There might be radiation belts inside the distance at which Voyager flew. There was a paper recently that has shown that maybe some of our initial ideas from the analysis of the Voyager data wasn't quite right. And basically, it was leveraging what we had learned with Cassini data about the Saturn magnetosphere and then applying it to Uranus and basically tweaking our models a little bit. But Uranus is very interesting. The magnetic field is tipped at a very large angle relative to the axis about which the planet is spinning, and it's offset. In other words, it's not centered at the center of the planet like our magnetic field or at Jupiter or Saturn. It's been offset. If you think of it as a bar magnet, that bar magnet is actually displaced. So very interesting to figure out just what exactly is going on. With Voyager, we just had a snapshot in time. So to go back with an orbiter and actually watch how that magnetosphere evolves and how it interacts with the wind from the sun with the solar wind will be very, very interesting.
Yeah, and there's also a mystery about the temperature as well. It's extremely cold, but it doesn't quite. It still ends up radiating more energy than it receives from the sun, as I recall.
Yeah, I think in the case of Uranus, it's all, maybe a little bit more, but in the case of Neptune and Jupiter and Saturn, they're radiating about, approximately twice as much energy as they receive from the sun, perhaps left over from their formation. But Uranus is closer to equilibrium. And we've noticed, when Voyager flew by Uranus, tipped on its side, the atmosphere was very bland and essentially featureless to what we could see in the cameras. But as the seasons have changed and because as Uranus orbits, then it goes from the South Pole near the sun to equatorial to ultimately the North Pole facing the sun and back again. And we've actually started to see more weather on Uranus as it's become tipped to an angle that's more not just the pole pointing at the sun, but more edge on.
Yeah, and that was another interesting thing from Voyager. At Neptune was a great dark spot that, as far as I know, is not there anymore. It dissipated. And you wonder if such a thing could happen conditionally at Uranus as well. Could you have a very large feature form up when it's experiencing more weather?
Yeah, astronomers have seen storms form on Uranus, maybe not as large as the great red spot at Jupiter or the great dark spot at Neptune. But you're right, that great dark spot at Neptune has dissipated, but they have seen other storms, maybe not quite as big, but other storms form on Neptune as well. And so we're learning a lot about atmospheric processes and can compare those processes between the various planets, and that the instrumentation and the telescopes that we now have today really provide us an even better look than we had, back in the 70s and 80s in the time of Voyager.
Now, with a planned Uranus mission, do you get from the planning of this? Do you get a full profile, meaning that let's look at Cassini and Saturn? In other words, Voyager was just that snapshot in time, but did Cassini get a complete picture? Do we have complete maps of all of the moons there? Did we get everything, so to speak?
Yes, Cassini really, in being there for 13 years and having a chance to study it, got complete maps of all of the icy satellites. Had a chance to be there for almost half a Saturn year and really be able to look at the weather and the seasonal changes that take place on Saturn, and seeing giant storms form, really study the hexagon, because Cassini's orbits were not just in the plane of the equatorial plane, but also we were able to change the shape of the orbit and move that so some of the orbits were looking at each pole, flying by each of the moons on different sides so that we could get complete maps and see their poles as well. Seeing both sides of the rings in a very special time geometrically where the rings were edge on to the sun. And we could actually look for anything sticking up above or below the rings, which we did during that time. And so really a chance to see everything in detail. But of course, Cassini, like every mission, left with a list of questions that we'd like to answer. One of which is, we see that Enceladus has this potential for life, but Cassini didn't carry life detection instruments per se. And so for a chance to go back to Enceladus, and also like Titan with Dragonfly, to carry the kinds of instruments that could perhaps answer that question. Here's Enceladus, a tiny moon. It's only 300 miles across, about a 1/7 the size of our moon. And yet out of the South Pole, in a series of 4 fractures we call tiger stripes, there are these jets shooting out like giant geysers, sending material, icy particles and vapor into space. And Cassini actually flew through those jets on Enceladus 7 times and sampled the icy particles and the gas itself. using instruments that were really there and, not expecting to do anything like that, but sampling it and telling us about the composition of that material and finding, carbon and hydrogen and oxygen and nitrogen and basically the key ingredients, the building blocks, the hydrocarbons, they're building blocks for life. And then having enough flybys of Enceladus, because that clearly became a focus of the mission once we saw the active South Pole, that there's a global liquid water ocean underneath Enceladus's icy crust, maybe 5 or 6 miles down. And that's going up through these conduits at the South Pole and coming out as shooting these jets into space. It's creating the E-ring. Enceladus orbits in the midst of a tenuous ring called the E-ring, and just so many things were answered about Enceladus, and yet that one question, is there life in the ocean of Enceladus? And if there is, that would be fascinating to find life so far away from the sun. And if there's not, if you've provided the conditions from which life could get started, and yet it didn't, that would be fascinating in and of itself as well. So I think at some point a mission to go back to Enceladus, the second planetary flagship in the decadal survey, is an Orbilander, something that would both orbit and ultimately land on the surface of Enceladus and make those measurements and follow up on what Cassini found.
I always found it interesting to make the comparison between Enceladus and Europa because, other than size, Enceladus, you look at the cracks in its surface where the jets are spraying out, and it's very blue and icy looking. Yet you look at Europa and it's dirty. Looks like it's all, the cracks, and it's all covered in tholins and things like that. So you wonder, compare these two moons. What are the differences that are causing such different yet similar features, but such wildly different colors?
Yeah, well, one thing about Saturn and Saturn's rings in particular, they are very good at blocking radiation. Saturn, in some ways, is a very radiation-free environment compared to the environment at Jupiter. There, you've got this harsh radiation hitting the surface and actually physically causing chemical changes in the surface that are causing the different colors and things that you see. In fact, if you were to stand on the surface of Europa, the radiation environment is so harsh that it would be fatal in a very short time. Whereas Enceladus, you could go and walk around on the surface of Enceladus, and it's a much different environment. So that has allowed some of the water ice to stay, I think, a bit more pristine. And then also you have a polluter there, the Jupiter system, if you think of it that way. The material from the Io volcanoes gets spewed out into space, and some of that goes outward and can end up on the surfaces of the moons as well. So Saturn, you have Enceladus, which is shooting out basically water vapor and a lot of mostly water products. So some of that does coat the other moons, but very different from being coated by all of the sulfur compounds and the other compounds that would come out of the Io volcanoes.
Yeah, and it's interesting how Io is doing that because it actually sort of wraps around Europa and lands. It doesn't land exactly where it's like ramming through it. It just sort of wraps around and falls on almost the back end in a way, and it's sort of forming a huge spot. So you wonder if that's been going on for the last 4.6 billion years. There's a lot of sulfur probably in that ocean, wouldn't you think?
Right. If it gets all the way from the surface down into the ocean, and that's an interesting question. Are we seeing material that's coming up through the fractures in the surface of Europa? Some of those linear features that are there is like water kind of coming up and then freezing in the cracks, or what's the process of overturning the surface, and how does that work exactly? And I think the Europa Clipper mission, which launched October of last year on October 14th and is now headed to Europa, will help us really better understand whether you have conditions that could support life at Europa, understand something about the ice shell thickness. If you'd ever want to return and drill through the ice shell, it'd be nice to know how thick it is. Can we tell something about the composition of the ocean? Does Europa perhaps have jets coming out in different places, maybe episodically, maybe not continuously like Enceladus, but are there jets of some sort? There are hints from some ground-based data that perhaps there might be something like that. And how does that ocean and ice shell interact? That what you're talking about, that overturn. Do you get material from the surface ultimately ending up back in the ocean? How does that work? What are those interesting surface features? What look like almost like little rafts of ice that almost look like they maybe were floating and then frozen in place. How does that work? How does the radiation change the environment on Europa as well? And can we tell about how salty, what the salinity of the ocean might be? And that's an important characteristic if you want to you can't have it too salty, for life. So lots of really good questions that will be addressed by Europa Clipper.
What does the instrument package of Europa Clipper look like as far as, being able to answer a question like, is there life there or not? Or is it just not quite that precision, just may not be able to do that, but can look for the conditions for it? What does the instrument profile look like?
Right. Some of the instruments, of course, they have cameras to study the surface, then instruments in the near infrared and far infrared, ultraviolet to do a lot of detailed remote sensing, a radar instrument on board that can perhaps penetrate through the ice and tell you something about maybe the ice-ocean interface. Lots of fields and particles instruments that can measure the interactions of all this radiation and the particles that are basically sped up in the radiation environment at Jupiter. So very diverse package. Of course, a magnetometer is along with the package as well. They'll be doing gravity experiments using the carrier signal. So really a full package, as Cassini had, a large variety of different instruments. And that's what you want to carry on a flagship mission.
When's it going to arrive?
I think it's 4 or 5 years. I'm not sure of the exact timing of when Europa Clipper is going to arrive.
I think a lot of people don't realize that's a long way to get to Europa in the Jupiter system, and even longer for Uranus. So the Uranus mission, should everything get greenlit and built, that's going to take years to get out there, right?
Yeah, for Uranus, it depends on the size of the launch vehicle, of course, that's available. But you're talking probably to get out to Uranus, something on the order of a decade or more to get all the way out to Uranus. The interesting thing about Voyager is what, really drove it. You think about it, Voyager launched in 1977, and that was really driven by the alignment of the planets at that time, that it was really a rare opportunity occurring over only once every 176 years, where you could visit all four of the outer planets with a single spacecraft. And so, Voyager launched in 1977, and of course it wasn't going to slow down and try and go into orbit. And that's what really lengthens, in a lot of cases, the time it takes to get there. You don't want to be going too fast. You have to slow down and go into orbit. So launched in 1977, and by 1979, both Voyager spacecraft were flying by Jupiter. A year or so later, it was Saturn, and in 1986, it was Uranus, 1989, Neptune. So it took 12 years to go from the Earth to Neptune.
Which is fast.
Fast, which is fast, and that they're both going fast enough that they're both now going out of the solar system. Voyager 1 going up to the north, and Voyager 2 headed down south of the ecliptic plane.
Now, Voyager 2, has that now left the solar system? In other words, is it past the line?
Yes, Voyager 2 left the solar system in 2018. So both Voyagers are now flying through interstellar space. Gravitationally, there's objects that are still bound to the sun. But as far as crossing the heliopause boundary, both Voyagers have crossed that boundary.
So what do the particles look like that you're detecting out in the interstellar medium as opposed to what they looked like before the heliopause?
Well, some of the interesting things that the Voyager in situ measurements have told us is that we saw the cosmic ray abundance really jump up for both Voyagers once we crossed the heliopause. And we knew that would probably happen. We just didn't know by quite as much how it would happen. The heliopause is essentially a very good shield against these high energy cosmic rays. You can think of them as radiation, and only about maybe 20 or 30% get through and actually get into our solar system, can reach Earth. And that could be very important in trying to understand how life can form in any planetary system, that radiation can be very damaging. And by studying our own heliosphere and its interactions, coming out from the sun, other stars have what they call astrospheres, basically heliospheres around them. And it could be important to understand those, to understand how life might be able to form on exoplanets that circle around other stars. Of course, Voyager is measuring electrons, protons, ions, good measurement of the composition of the cosmic rays of, not only of hydrogen and helium, but elements up even heavier all the way out to iron, measuring the magnetic field. And the interesting and intriguing thing is that the two Voyagers, after crossing the heliopause, the thought was that the magnetic field direction would rotate from the solar direction into the interstellar direction. And yet, for both Voyagers, that hasn't happened yet. So we're wondering if there's some intermediate region, perhaps, where we're still under the influence of the sun. And so both of the Voyagers are watching and waiting to see when and if that magnetic field will rotate into the interstellar direction. We can measure the plasma density in interstellar space, look for what we call shocks or pressure fronts, these effects from these, like coronal mass ejections or something that come from the sun and then propagate out and actually their effects cross through the heliopause. So it's just really nice to be there, to be directly sampling what you can think of the ocean of interstellar space is like in relatively close to our star, but just a very different place, an unknown place, a place to explore and to better understand.
It is. It's sort of a map of the influence of the sun that the Voyagers have built and sort of constrained. And it sort of leads to a situation of bonus science from two spacecraft that are long past their primary mission into I would imagine, unplanned mission, in mapping the influence of the sun in the very, very end and the beginning of interstellar space, the end of the solar system and beginning of the interstellar medium. And it's all a bonus. It's all for free. Now, health for the spacecraft. How much time is left for each one until they just don't have the voltage anymore to continue?
Yeah, that's a good question, because there are clever things that we've been doing along the way to extend the lifetime of the mission. And I would just say I was, privileged to be there at the launch of the Voyagers. And I remember with each of the planetary flybys, by the time we got to Neptune, the feeling was, oh, we are dealing with two very old spacecraft. And that was in 1989. And everyone was saying, oh, they're only going to last 2-3 more years. And so they really staffed the project down. But those two spacecraft, like little Energizer bunnies, just keep going and going and going. And so to get to your point, we're now where we've turned off most of the redundant engineering systems that we could safely turn off for each spacecraft. And now we're entering into a phase where we're having to turn off instruments on the spacecraft. In the next year or so, we're going to start to turn off. We have a pair of particle instruments, the cosmic ray instrument and the low energy charged particle instrument. We'll turn off a different one on both spacecraft. The goal is to try and keep, as large a variety of instruments flying between the two spacecraft now. And if we turn those instruments off, we'll gain another year, maybe year and a half of life for each spacecraft. And so we'll slowly then be turning off instruments, and then we'll start to try perhaps little sportier things, start turning off some of the heaters on some of the engineering subsystems, like the heater on the sun tracker, and see what will happen there. But just realize that as we go down this path, there'll probably reach a point where we'll have something happen that we won't recover from. And there might be a day when we'll listen for Voyager and there won't be a signal, there won't be a carrier tone, and there just won't be any indication that the Voyager is there, because perhaps something has happened or the power has just dropped too low, and that will mark the end of the mission. But we're really, we're really hopeful and expect that we'll make it out to our 50th anniversary, and that'll be in the fall of 2027, 50 years from launch for each of the Voyager probes, and we think it's very likely to make that milestone. But you never know. You've got two aging spacecraft, and a lot could happen just in that short time to the 50th anniversary.
All right, Dr. Spilker, thank you for joining us today. I always found it really interesting that the Voyager record, Saturn's rings, ended up resembling a phonograph record.
It's true, yeah.
It was sort of even Saturn was waxing poetic, apparently. But I hope you'll come back and update us on Voyager 1 and Voyager 2 as things go on, and also ice giant and gas giant science and rings.
Right. It would be a pleasure. I enjoy talking about my two favorite missions.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.